So constant pressure calorimetry. So we just discussed how we calculate enthalpy of a reaction at constant pressure. We've talked about the bomb calorimeter, where the volume was constant. The bomb calorimeter was kind of a complicated looking thing. This is what we often refer to as a coffee cup calorimeter. This is extremely low tech, right? 2 styrofoam coffee cups. This one's fancy. It's got a cork lid. We're going to use pieces of cardboard with holes cut in them. Glass thermometer, glass stir rod, or sometimes we even use the thermometer to stir it. Very, very low tech. This is not constant volume because gases can escape from this, but it's constant pressure because gases can escape from this. Okay? So for lots of aqueous reactions, we're going to use constant pressure calorimetry. So in this situation, what we've got going on here is Q for the solution, the heat exchanged by the solution is going to equal the mass of the solution times the specific heat capacity of the solution times its change in temperature. So the solution is the aqueous solution in the calorimeter. The chemical reaction happens in the solution. We're not putting dry chemicals together here and mixing them up and having something happen. We're having 2 solutions mixed together and have something happen. So it's impossible to measure the temperatures of the reactants because they're in the water. The chemical reaction occurs in the water. It absorbs heat from the water or it releases heat to the water. But we can measure the temperature change of the water, right? So we can measure the temperature change of the solution. The heat, if the reaction is releasing energy, come on, pointer. Oh, that's great. No matter where I point, it's in the same place. The universe hates me. Maybe if I do this. No, it's stuck. Awesome. The heat absorbed or released by the reaction is equal to the heat released or absorbed by the solution, right? We've talked about that before. So there's heat being exchanged. It's going from one thing to the other. The amount is the same. The sign is different. Well, the heat of reaction is equal to Q at constant pressure. That's equal to Q for the reaction. If we want to know, delta H per mole so that we can write it with a balanced chemical equation, then we're just going to divide by the number of moles of substance that reacted. We measure it out in mass. We know what it is. We find the number of moles. So that's the big idea here. Let's do a problem. So the addition of hydrochloric acid to a silver nitrate solution precipitates silver chloride according to this reaction. Nice. When 50 milliliters, that's awesome. When 50 milliliters of 0.100 molar silver nitrate is combined with 50 milliliters of 0.100 molar HCl in a coffee cup calorimeter, the temperature changes from 23.4 degrees Celsius to 24.21 degrees Celsius. Calculate heat of reaction as written, for the reaction as written. Use 1 gram per milliliter as the density of the solution and specific heat capacity of 4.18 joules per gram degree Celsius. Okay, there's just lots of stuff there, right? We need to calculate delta H. So coffee cup calorimetry, constant pressure, delta H for the reaction equals the Q at constant pressure. Well, the Q at constant pressure in this situation is the heat absorbed or released by the chemical reaction. We can't measure that, but the heat released by that goes into the solution. So that's equal to negative Q for the solution. Okay? if we look at the temperature here, the solution temperature went from 23.4 to 24.21. That's going up. So the chemical reaction, is this exothermic or endothermic? It's exothermic. The reaction is giving energy to the water, and that's why the solution temperature goes up. We can't directly calculate, oh, it's back. We can't directly calculate this, but we can calculate this. Q for the solution is mc delta T, right? So I'm going to calculate Q solution. Q solution equals M solution C sub S for the solution and delta T for the solution. Well, did they give us the mass? No. They gave us molarities and they gave us volumes. At this point, the molarity doesn't matter. We're trying to find the mass of the solution. There were two things put together in this cup, 50 milliliters of this thing and 50 milliliters of that thing. So what's the total volume? 100 milliliters. So we have 100 milliliters of solution, 100, and when we've got a decimal point and one decimal place there, 100 milliliters. To convert volume to mass, we need the density. They're telling us to use 1.00 grams per milliliter as the density. So we use the density to convert from milliliters to grams. So that's just equal to 100.0 grams. So that's taking a previous concept of converting volume and mass with density and hiding it inside this problem. So that's our mass, the mass of the solution. So 100.0 grams. We need the specific heat capacity of the solution. So we're told to use the specific heat capacity of water for this solution. It's mostly water, so that's very reasonable. So 4.18 joules per gram degrees Celsius. And then we need the temperature change. There's just really not a lot of room here. Delta T, it's always the final minus the initial. So the final temperature is 24.21, and the initial was 23. That's not a 2. Christian gets a little excited sometimes. (24.21) minus 23.4, 0.81 degrees Celsius. That's my temperature change. When I screw up, be sure to tell me. When I screw up, not if. Let's look at the units. Grams cancel grams, degrees Celsius cancels degrees Celsius. I'm left with the unit of joule, which is great because that's a unit of energy. So I have 100 times 4.18 times 0.81. So Q for the solution equals 338.58 joules. How many significant figures in that result? 2. The temperatures each had 4 sig figs, but when we do the subtraction, we end up with 2. So I'm going to underline the second digit there to remind myself. So I calculated Q solution. So the heat of reaction equals negative Q solution, right? So that would be negative 338.58 joules. That's a 3. The reaction as written. So this reaction has 1 mole of silver nitrate reacting with 1 mole of HCl. It matters how much reacts. If you have more react, the energy change will be larger. So, do we have 1 mole of silver nitrate reacting? We can't tell just like eyeballing it. Well, how could we figure that out? Well, we have the volume and we have the molarity. Could we figure out how many moles of silver nitrate were in the cup? Sure we can. I'm going to do this in blue because maybe it'll be a little less confusing. So I've got 50.0 milliliters, and then I've got molarity 0.100 moles per liter of the silver nitrate. Well, the milliliters and the liters aren't going to work out very well, are they? So let's convert this milliliters to liters. So we can move the decimal point over 3 places. Or what I could do is instead of writing milliliters, I could write times 10 to the minus 3 liters. Because that's what milli means. I could do it that way. So 50 EE minus 3 times 0.1. So I have 0.00500 moles of silver nitrate. You could also write this as 0.0500 liters. It's the same thing. Any questions? We should do it for the other one as well, because what if there's less than that of this, right? But if we look at the volume and the concentration, it's going to be the same, isn't it? 50 milliliters times 0.1 molar, it's going to give us the same number of moles of HCl. So those are equal, so we could use either one because they're the same. So it's that many joules for this many moles. I want to know for 1 mole. So I'm going to divide by the number of moles in the problem. 0.00500 moles. And so I get this big old number. And that should only have 2 significant figures, and the unit there is joules. It would be joules per mole. You have to be a little careful. What this is saying is that delta H for this reaction, normally, since this is a big number, we would make that into kilojoules. So this, let's finish our rounding here. So this would be 68,000 joules, or 68 kilojoules. So normally we'd say delta H for the reaction is minus 68 kilojoules. It's this amount of energy for 1 mole of this, for 1 mole of that, for 1 mole of this, for 1 mole of that. But you need to be careful, because if this was 4 moles, then it's not per 1 mole, it's per molar amount of each substance, reactant, or product in the equation. So you got to be a little careful.
You said if it's what?
Pardon me?
You said if it's what?
Well, it's this amount per this many moles. So here it is per 1 mole. If we look, let's see if I can find one. If we look at this reaction, maybe if I write something, now will it let my pointer move? No. Look up there. That delta H, minus 906. Minus 906 kilojoules, is that per mole?
Yeah.
Not exactly. It's per 4 moles of ammonia, per 5 moles of oxygen, per 4 moles of NO, and per 6 moles of water. It depends on what the coefficients are. So you have to be a little bit careful with that.
I was wondering why you said no.
I said no because it's all caps. It's yelling, right? Yeah, it's one of my favorite words. No, you can't get that app that's for 17 plus. Yeah. Because that just happened. Okay, so any questions?